Well, we have made it. We are finally to our last section in our Algebra 1-2 curriculum. Our goal is to be able to compare different functions, whether they be linear, straight lines, exponentials like the L's or J's, or quadratics like the U-shaped parabolas. Your objective is I will be able to compare linear, quadratic, and exponential functions. We have done this in previous units as well, but we just want to make sure we can tie it all together one last time. So look at this first example. You have a linear, g of x is our straight line, f of x is our parabola. So just to make sure we're good here, the parabola, I'm going to put in red, is our f of x, and the straight line is our g of x. So just to make sure we're good, so we can see that visually. So f of x is our red, and g of x is our blue. All right, here we go. First thing we want to do is compare the y-intercepts. So the y-intercept of the straight line for g of x is right here at -2. And the y-intercept for the red parabola is just above it. So that means f of x is less than, it is not less than. We're looking at about -2 for g of x and -1 for f of x. So let's look at that. That's -1 and that's -2. If we want to compare that, -1 is less than, is greater than -2. Not sure where my mind is today. -1 is a smaller negative number, so it's greater in value. Now, the next question we want to look at is where f of -1 occurs. So when x is -1, the parabola's point is right here. When x equals -1, the straight line's point is down here. So that gives us a point of about +2 for f of x and about -1 for g of x. So 2 is greater than -1. So it looks like up until there, going from the left towards the center, that f of x tends to be greater. Now let's just get some basic information. Let's look at the x-intercepts here. Let's do f of x first. How many x-intercepts does it have? It has 1, 2. How many y-intercepts does it have? Just 1 right there. Now let's look at the approximate x-intercepts. They're located at -1, 2, 3, 4. Looks like it's at about -4. And then the other one is right about the origin, 0, 0. The approximate y-intercept looks right about 0, -1. The approximate maximum right here, the highest value that parabola reaches, is a +3. So the vertex is located at -2, +3. That is our vertex. The domain, that graph goes forever to the left, -∞, forever to the right. So it's going forever to the left, and it's going forever to the right. Now range, we want to know how low does it go. Well, again, it's going down, down, down forever, so it's going for -∞, but how high does it go? Well, it reaches that point right there, which was +3, which was the number from our vertex above. So now let's take a moment and look at the straight line for g of x. It has only one x-intercept right about here. Trying to get my pen to write it. It has one x-intercept right about there, about -1.5. So it only has one, and it's right about -1.5. Let's look at the y-intercept. It intersects the y-axis right about -2. And it only had the one y-intercept. Approximate maximum, well, it goes forever up and to the left and it goes forever down to the right, so there is no maximum value. Its domain is just like f of x. It goes forever to the left and forever to the right. And what's cool about the lines is its range also goes as low as it can go forever to as high as it can go. So negative infinity to positive infinity again. Now, one question over here I want to make sure we don't miss, letter C, says, what is the approximate points of intersection? So we seem to intersect here, and we seem to intersect right about here, and we're estimating. The coordinates of that point on top is -3, +2, and the lower one seems to occur right about 0, -2. Once you have the graphs and the tables set up and down and in your notes, go ahead and move on. We just have one more example, and that is it. You will officially be done taking your notes. All right, here we go. This is where we're going to make our tie into geometry to get you ready for next year. The length of a rectangle is 21 inches more than twice the width. The area is 50 inches squared. The first thing I would like you to do is draw a rectangle. Let's look at the information they gave us. The length of the rectangle is 21 more than twice the width. 21 more than twice the width. Well, do we even know what the width is? We have no idea, so let's name the width. Let's call it x. You could call it w for width, but I'm going to go with x. So now our length is going to be 21 more than twice the width, 2 times the x. So now we have labeled our rectangle. It has a length of 21 plus 2x and a width of just x. We want to write a function that represents the area of the rectangle in terms of width. Well, remember, area equals length times width. The length is 21 plus 2x, and the width was just x. Ooh, there is something outside parentheses. Whatever shall we do? Let's go ahead and distribute. 2x times x is 2x squared, and x times 21 is 21x. So that is our area as a function. So we could say that is equal to y. Now use the function in part B to solve for the width. Well, the fact is we know that it has an area of 50 inches squared. So that means we know that 2x squared plus 21x is equal to 50. The y was the area. Ooh, that looks like a quadratic equation. I'm hoping that you're thinking, ooh, it's not set equal to 0. So the first thing we need to do is move the 50 over to the other side. And now we create the equation 2x squared plus 21x minus 50 equals 0. Now that is in standard form. We have a couple choices. Do we want to try and factor it, or do we want to go right to the quadratic formula? Well, let's take a moment and think about that. Can we think of two numbers that multiply to a times c, which is -100, that add to 21? Well, let's see. 10 and 10 is 100, but 10 and 10 does not add to 21. We could do 5 and 20, 50 and 2. I'm not coming up with a combination. So this looks like we're going to have to use our quadratic formula. So what I'm going to do to make some space is I'm going to rewrite this equation so that we can see it, and then we are going to go into our quadratic formula. We have 2x squared plus 21x minus 50 equals 0. We will go ahead and put that into our quadratic formula. All right, so we're going to start subbing it in. X is equal to negative b, so negative 21, plus or minus the square root of b squared, which would be 21 squared, minus 4ac times 2 times negative 50, all over 2a, which is 2 times 2. Let's simplify that down. We have negative 21 plus or minus 21 squared, so 21 times 21, equals 441. And then remember, we're doing 4 times 2 times 50. Well, 4 times 2 is 8. 8 times 50 is 400. And a negative times a negative is a positive 400. All over 2 times 2, which is 4. So let's continue. We now have x is equal to negative 21 plus or minus the square root of, we're going to add the 441 and the 400, which is 841, all over 4. Now, the square root of 841, if we put that in our calculator, is 29. That is actually a perfect square. That works out just lovely. So we have x is equal to negative 21 plus or minus 29 all over 4. So if I were to continue simplifying, negative 21 plus 29 all over 4. So negative 21 plus 29 is 8. 8 over 4 is 2. That means one of our values is x could equal 2. But now, that was negative 21 plus 29. Let's see what happens if we do negative 21 minus 29 over 4. Well, negative 21 minus 29 is negative 50. Negative 50 divided by 4 is a negative 12.5. So x could equal a negative 12.5. Now let's stop and think for just a moment. Does that seem reasonable? Could our width be a negative value? Could we have a negative 12.5 inches? The answer is no, we cannot. So the solution where we did minus 29 is not a valid solution. So when letter B says find the width, we're going to stick with x equals 2. That is our only value that is possible. So the question C, just to finish up, what are the dimensions? Remember, our length was 21 plus 2x. Well, we now know that x is 2. Well, 21 plus 4 is 25. So 25 inches. The width was just x, and x was 2. So our length is 25 inches, and our width is 2 inches. Now that is taking algebra all the way through to the end of the curriculum and applying it to geometry questions that you are guaranteed to see next year in your geometry classes. So take a moment, see how that feels. We applied the quadratic formula to a real-life situation with our rectangle. If you feel comfortable with how everything went, then you are good, you're done, you're ready for your assignment in class. If you'd like to rewatch or review the questions, take a moment and make sure you are comfortable with it.